All right. So we got a little bookkeeping kind of thing to do here before we start class. Right now, we are at the steady state sinusoidal lecture 4, where it says instantaneous power and average power, which is supposed to be, the lecture is supposed to be given next Monday, but I'm going to do this today. On Monday, I have to leave class at 11:30 because of ABET junk. And I'm not sure whether or not I will have to leave class early on Wednesday as well because of ABET related stuff. So what I would like to do Monday is only teach multi-frequency power and then give you guys the rest of the class period off, because effective values and complex power are reviews of material that is covered in circuits 1. So I don't think we'll have to spend a whole heck of a lot of time on that. So Monday, 30 minutes to class, then I gotta go, so you guys could watch videos or you can leave, whatever you want to do, but I can't be here. So I just wanted to make you aware of that. It looks like still be able to stay, I think, roughly on course. So we should still be able to keep exam 2 on Wednesday the 3rd, so that you can have it and get it, at least the in-class portion, back to you before the drop date, which is Friday the 5th. We could potentially move that exam up if you guys wanted to, but I'm happy leaving it where it is. So we could move it up to the 1st because we're ahead, or we can leave it on the 3rd. Anybody got any thoughts on that? Anybody got any other exams that are going to screw things up or anything?
I sort of just align myself like preparation of the exams. I align myself with like homeworks. So if you put the homeworks, I don't know how many homeworks get planned, but if you have like 5 homeworks that if you did move the exam up, that would need to be crammed in like a week and a half. That probably won't work for me. But if there's only like a couple homeworks before the exam, that's fine.
So let me think about this. There is a homework assignment that I need to put up today regarding instantaneous power, average power, and maximum average power transfer. And I think it also covers.
I'd also prefer if the test wasn't on the 1st, because I have another exam.
Okay.
Oh, I didn't think about that. I might as well.
Yeah. All right. We'll leave the exam on that Wednesday then. I'm trying to think of how many homeworks we're going to have between then. I think it's 3. So the homework 15, but it's not 15 anymore because I think I actually missed assigning one. It's not that big of a deal. Is going to cover complex power and power factor correction. And I think effective values as well. Homework 14, I think, is instantaneous power, average power, and maybe a multi-frequency power problem. I'll have to look. But I think it's only going to be 2 to 3 homeworks tops before the next test. All right, so let us start talking about what we need to talk about today. All right. So the first thing that we are going to discuss is instantaneous power. And as I said previously, this part is entirely review from circuits 1. So we're going to cover it reasonably quickly. So if I have the following circuit, here is some voltage Vs of t, and it is being applied across a linear black box network. Meaning that the network is comprised solely of linear components. So that would be independent and dependent voltage and current sources, capacitors, inductors, and resistors. I can determine the power that is absorbed by this linear black box network by simply taking the product of the voltage drop across our network and the current flowing into our network. So what I am suggesting is that P of t is simply Ix of t times Vx of t. Nothing remotely new there. That is literally the first day of circuits 1 stuff. V is equal to I of V. Now let's say that Vx, the voltage drop across our linear black box network, is a sinusoidal voltage. So we have Vm, the magnitude of the voltage, cosine omega t plus some phase angle theta v volts across our network. And let's say that our current flowing through our network is then also sinusoidal, and it's of the form Im cosine omega t plus some phase angle theta I. Well, that tells me that the instantaneous power, or power as a function of time, absorbed by my network is the product of those two waveforms. All right. When I multiply two sinusoidal functions together, there's a specifically two cosine functions together. There's a trigonometric identity that I can apply that will simplify things a little bit. That trig identity is cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. In this case, we're going to consider angle 1 omega t plus theta v and angle 2 omega t plus theta I. And what we will get is then 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So this is our generic expression for the instantaneous power absorbed by a circuit element, or looking into the terminals of a one-port network, or however we want to define it. This works for literally any and everything as long as it's a linear black box network containing two terminals. I believe in circuits 1, I went through the showed videos about how you could simplify this expression for resistors, capacitors, and inductors. So I won't worry about doing that here. I want to point out that this instantaneous power has a DC term, right? Because Vm, Im, theta v, and theta I are all constants. So when we multiply all these things out together, recognizing that cosine of theta v minus theta I is simply going to be a number ranging from +1 to -1. That just gives us a constant value. And then we have our high frequency twice omega AC term. So generically, if we plotted power as a function of time for a generic network here, it's going to look something like this. So it's a waveform with a frequency of twice omega that has a DC offset. Well, a DC offset represents the average power absorbed by that load. And the AC portion is simply the deviation from that offset as time progresses. We can mathematically prove that our expression 1/2 Vm Im cosine theta v minus theta I also represents the average portion of the power. By defining and understanding what the average value of the sinusoid means. So if I have a periodic signal, x of t, the average value of x will be defined as the integral of my periodic function over exactly one period. So I'm going to choose to represent that as measuring from 0 to t, where t is the amount of time it takes for exactly one cycle to occur. When you're doing homework problems and stuff like that, it may sometimes be useful to integrate from some specific point in time to exactly one period later. So you may represent that as negative capital T over 2 to positive capital T over 2, or 0 to capital T, or somewhere in between. It doesn't matter, but you can kind of move those limits of integration to suit your problem of interest. So we integrate, we integrate our periodic function over exactly one period, and then we have to also divide that integration by the period itself. So if we take the area under the curve and then we divide by the time it takes for one cycle to occur, we get an average value for that periodic function. So for our power function, that is going to be one period, we'll work on that momentarily, from, let's call it 0 to t, of 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. And I am going to split this up into two integrals. But before I do that, I want to figure out what the period of this generic waveform is.
And so what I mean by that is we know that omega is equal to 2 pi times the linear frequency of our signal, right? Because our power function is operating at twice omega of whatever the voltage or current is, we could simply multiply this guy by a factor of 2. And recognizing that the linear frequency is simply 1 over the period t, we get twice omega is equal to 4 pi over t, which then gives us omega is equal to, sorry, t is equal to 2 pi over omega. So that's our periodicity here, which we would have got the exact same result if we'd only considered omega itself. Well, the way these things work out, when you have an integer multiple of frequencies, it all boils back down to this fundamental relationship. So that's going to give us 1 over t is omega over 2 pi integral from 0 to 2 pi over omega 1/2 Vm Im cosine theta v minus theta I dt plus integral from 0 to 2 pi over omega of 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt, and I'll close my brackets here. All right, so first, does anybody have any issue whatsoever with me splitting this into effectively 2 integrals, right? I mean, I have simply a additive combination of functions, and so I should be able to integrate each part and add the results together and get the exact same result. And that works because this is a linear system. So again, we can notice that 1/2 Vm Im cosine theta v minus theta I dt, or excuse me, without the dt is just a constant value. So if I integrate the constant value over a specific time period, and then I divide by the duration of that time period, what do I get? So if I integrated, let me draw here. So as a quick aside, I have a function. And it has a constant value. Let's say, for the sake of argument, 5 volts. And I choose to integrate it from, I can't see that, which means you guys can't see that. This time x1 to some later point in time x2. Pardon? I can't hear you, I'm sorry. Oh, that color doesn't show up well either. Okay. Let me do this a third time. Purple. Can you guys see this one? Okay. So if I integrate this constant value signal with these limits of integration, what am I going to get? I'm going to get a number. When I divide, so I'm going to get, say, 5 volts times x2 minus x1 in this case, right? Well, when I divide by x2 minus x1, the duration, I'm left with just the value of the voltage signal itself, 5 volts. So the results of my integration here will be simply 1/2 Vm Im cosine theta v minus theta I plus, now I have omega over 2 pi times the integral from 0 to 2 pi over omega of this guy, 1/2 Vm Im cosine omega t plus theta v plus theta I dt. Well, what I'm doing in this second part, and I'll write it up here. So I just have the AC term, right? I'm integrating this sinusoidal function. I'll do it in green. Over exactly one period. So here's x1, here's x2. So when I integrate a sinusoidal function over exactly one period or any integer number of periods, what happens? It goes to 0, right? The area above the x-axis exactly cancels out the area below the x-axis. So this whole thing goes away. So I'm left with the exact same result I got previously, right? So we proved it graphically and intuitively, and then went and done it using mathematics as well. All right, so any questions on instantaneous power or average power? Any thoughts, comments, concerns? Again, this should be largely review. All right, nobody's willing to say anything, so now let's move along to maximum average power transfer. All right, so in a DC circuit, let's start there with a very quick refresher. We learned that we could convert any two-terminal DC network into a practical voltage source using Thevenin's theorem. So here we have VTH, here we have RTH, and if I connected a load RL to that practical voltage source representation of my DC circuit, where this is the voltage drop VL, which occurs over my load, and this is the current IL that's flowing through my load, I can say that the power absorbed by the load is simply the product of VL times IL, which is, let's see, VTH divided by RTH plus RL multiplied by RL. So I'm doing simple voltage division to get the voltage drop over just the load resistance. And I'm going to multiply that by the current. And so the current IL would be VTH divided by the series resistance seen by the source, RTH plus RL. And so let me do just a smidge of math here. We have VTH squared RL divided by the quantity RTH plus RL squared, right? That's the instantaneous power, excuse me, the power absorbed by my DC load in this case, which would be instantaneous and the average power because it's constant value. we were able to determine the value of RL, which caused maximum power transfer to occur, by taking the derivative of this with respect to RL and setting it equal to 0. So the derivative with respect to RL of VTH squared RL divided by RTH squared plus RL squared and equals 0 revealed to us that average or maximum power transfer occurs when RL is exactly equal to R Thevenin. We can describe that graphically as such. So here is the power absorbed by our load. Here's our values of RL. So when our load is a short circuit, we know that no power is absorbed. And similarly, when our load is an open circuit, having infinite resistance, no power is absorbed. And in between those 2 points, our curve looks something like this, where the maximum value occurs when RL is exactly equal to R Thevenin. All right. Well, what we are about to do is figure out what happens when, instead of having a Thevenin resistance to deal with, we have a Thevenin impedance. Okay. So in the frequency domain, our system looks slightly different. We have a phasor Thevenin voltage VTH connected to some Thevenin impedance ZTH, and we are trying to figure out what value of ZL causes maximum power transfer to occur, where this is our phasor voltage VL, and this is our phasor current IL. So we know that our phasor current IL, in this case, is nothing more than our Thevenin voltage VTH divided by our Thevenin impedance plus our load impedance, right? I am going to go one step further here, and I'm going to say that this is the same as this expression, right, where I'm simply expressing my impedances in a rectangular format, right? Because that's going to help me identify a way in which to maximize this quantity. Similarly, the voltage drop over my load, I can get, again, using voltage division, where that's going to be VTH times ZL divided by ZTH plus ZL. And again, I will express this in terms of the resistance and reactance of my impedances, giving me RTH plus JXTH plus RL plus JXL in my denominator, and I will have VTH times RL plus JXL in my numerator. All right, so now what I'm going to do is I'm going to determine the magnitude of my load current and the magnitude of my load resistance, okay? So these are complex numbers. Does anybody remember how I get the magnitude of a complex number?
You put it into
So Pythagorean theorem effectively does work. So it's the square root of the real part squared plus the imaginary part squared, or I can simply multiply it by the complex conjugate of the number and then take the square root of that. Both give me the exact same thing. So if I, let's see, use those definitions, I can see that the magnitude of my phasor current IL is going to come out to be the magnitude of my Thevenin voltage divided by my Thevenin resistance plus my load resistance squared plus my Thevenin reactance plus my load reactance quantity squared. And then I take the square root of that. So that's the, multiply it by its complex conjugate and then divide by, or excuse me, take the square root, right? So if I have ZTH plus ZL multiplied by the complex conjugate of that, just as a quick aside so that we can prove it in case any of you guys have questions. What I'm doing is I'm taking the square root of this guy right here, right? So my cross multiplication terms are going to go away because I'm going to have a plus j blah, 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 and a minus j blah, blah, blah. I'm only going to be left with purely real things. So I'm going to have RTH plus RL quantity squared, and then XTH plus XL quantity squared, square root of that. All right. Similarly, the magnitude of my load voltage will be the magnitude of VTH times RTH, sorry, no, RL squared plus XL squared to the 1/2 power, and the exact same denominator as before. So I'm literally just going to write denominator down here because I'm kind of running out of space. All right. Now you may be asking yourself, why the heck am I doing this, figuring out what the magnitude of IL is and the magnitude of VL is? Well, the magnitude of IL is IM by definition, right? And the magnitude of VL is Vm by definition. So what I'm actually doing right here is I'm building the parts of my average power equation, because I need to figure out what my average power is going to be. So I figured out what Vm is, I figured out what Im is, and now I need to figure out how to write cosine theta v minus theta I in terms of what I know. So to figure that out, let's look at an impedance in the complex plane. So this is the imaginary axis. This is the real axis. Here's my angle, theta z. Here's my magnitude, let's just call it ZL for the sake of argument. Here's RL. And here is XL, right? Well, my impedance by definition, ZL, is the ratio of my phasor voltage VL divided by my phasor current IL, which means I have the magnitude of VL divided by the magnitude of IL with a phase angle of theta V minus theta I, where theta V minus theta I is theta ZL. So if I take the cosine of that angle, I'm just left with the real portion, right? So I can say that cosine of theta ZL is going to be the real bit RL divided by the magnitude of my impedance, which is RL squared plus XL squared square root. Right, just good old simple trig identities. Cosine is adjacent over the hypotenuse, where the adjacent bit is RL, and the hypotenuse is the square root of RL squared plus XL squared. So if I plug all of these relationships in, my average power equation becomes 1/2 times, so what do I have here for Vm? The magnitude of V Thevenin times this guy divided by power. So that is V. Now I need to substitute in Im. So I'm going to have that exact same denominator, RTH plus RL squared plus XTH plus XL squared, whole thing, square root. Up here, I simply have the magnitude of V Thevenin. So that's Im, and now I need to multiply by the cosine of theta V minus theta I, which is RL divided by RL squared plus XL squared to the 1/2 power. So what's this going to leave me with? Well, I have a factor of RL squared plus XL squared to the 1/2 power in the numerator and the denominator. So that bit's going to go away. So this guy exactly cancels out this guy. In the denominator, I have the Thevenin resistance plus the load resistance squared plus the Thevenin reactance plus the load reactance squared. The square root of that multiplied by itself. So those two square roots are going to cancel each other out. So I'm going to have something like 1/2. And then down here, I'm going to have RTH plus RL squared plus XTH plus XL squared. And in my numerator, I should just have the magnitude of my Thevenin voltage squared multiplied by my load resistance. So this is the function that we are trying to minimize. All right? So whenever, excuse me, we are trying to maximize. So whenever this function is at its maximum, maximum average power transfer occurs. So let me ask you guys a question. What do the reactances do? So it doesn't matter, notice that it's the square, right? So it doesn't matter if my reactance terms result in a positive value or a negative value. When I square it, it always serves to make my denominator larger, which in turn makes my power transfer smaller, right? So maximum average power transfer will occur when XL is exactly equal to negative XTH. Does that make sense? Let's start there, all right? So where did I put my pen thing? Here we go. So maximized when XL is equal to negative XTH. So under that condition, we are left with 1/2 RTH plus RL squared divided by the magnitude of our phasor Thevenin voltage squared times RL. Now we want to figure out what makes this its maximum value. But this expression should look familiar. If we scroll up a little bit here, in our DC circuit, we were maximizing the expression V Thevenin squared times RL over R Thevenin squared plus RL squared quantity squared. That is the exact same thing we are maximizing now, except it's multiplied by a factor of 1/2, which, because we're trying to set it equals 0, that factor of 1/2 does nothing. So we can maximize that portion by setting RL exactly equal to RTH. Putting these two things together, we can say then that maximum average power transfer occurs when ZL is equal to RTH minus JXTH, or simply the complex conjugate of the Thevenin impedance. So we got 30 minutes left. Let's work an example problem illustrating this property. So let's say that I have the following circuit. I want to figure out two things. A, what value of ZL causes maximum average power transfer? And B, what is the max average power transferred? All right. So just for the sake of argument, here's VL and here's IL. So what do I need to do in order to answer either of these questions? All right. So all right. So I believe what you're suggesting is that I find the Thevenin equivalent of everything that's connected to our load impedance in so many words. All right. So how do we find the Thevenin impedance of the network to the left of ZL? Anybody remember? We got to disconnect our load impedance first off, and then we are going to, so 2 ohms, J 1 ohm, 4 ohm, so we've disconnected our load impedance, right? What does this allow us to determine? Not making any modifications whatsoever. By definition, the Thevenin voltage is the open circuit voltage drop across those terminals, right? So let's talk about how we can figure out what that Thevenin voltage is. Yeah, finding the Thevenin resistance would be easy. All right, so we could do that. So the Thevenin resistance, how do I do that? What do I do to my source? We're finding the Thevenin impedance now in this case. We always need to be looking at a dead network, which means we have to turn off all of our independent sources. So to turn off that independent current source, do I short circuit it or do I open circuit it? Open circuit, right? Because I want to make sure that zero current is flowing and no current flows to an open circuit. So that means my Thevenin impedance is simply found by looking in to this guy. So what are we going to have? So to me, it looks like a 4 ohm impedance in parallel with a 2 plus J1 ohm impedance, right? So 4 ohms times 2 plus J1 ohms over 4 ohms plus 2 plus J1 ohms. And let's see, where did I put my calculator? Right here. .470 with an angle of 17.103. Does this make sense? Anybody tell me why it does or does not make sense? So it makes sense to me because the phase angle is positive, and I would expect a positive phase angle for an inductive load. And since my load is comprised only of resistors and inductors, I will definitely have an inductive load there. So nothing particularly surprising there. All right, so from this then, what value of ZL causes maximum average power transfer to occur? Don't even need to do that, right? Maximum average power transfer occurs when ZL is equal to the complex conjugate of Z Thevenin. If we know what Z Thevenin is, we just found it, we simply need to take the complex conjugate. How do I take the complex conjugate of this number in polar form? Negative of the angle. Change the sign of the angle would be a better way to put it. Yeah. So that would be 1.470 with an angle of negative 17.103 degrees ohms. So this is our first question answered. Now to determine what the value of the maximum average power transferred is going to require us to know either our Thevenin voltage or our Thevenin current. We already have the circuit up here to find our Thevenin voltage, or we could find our Thevenin current, or Norton current, I guess would be a better way to express it. So you guys want to work with what we have, or do you want to find the Norton current? Norton current, meaning I would short circuit this guy and then figure out what that phasor current is. Which one seems easier? Pardon? I honestly would argue that finding the Norton current is easier here. Can anybody tell me why? It shorts out that 4 ohm resistor, meaning we can just do simple current division to figure it out, because we know that all of the current that flows through that J1 ohm impedance will flow through that short as well. So I Norton is going to be 4 angle 0 degrees amps times 1 over J1 divided by 1 over 2 plus 1 over J1. So let's see here, 4 angles 0, 1 over 1i, 1 over 2 plus 1 over 1i. .578 with an angle of negative 26.565 degrees. All right, so how do we calculate our power here? let's take a look back here, right? I think this guy here tells us exactly what we need to do, right? So when RL is exactly equal to RTH, maximum power transfer occurs. So we could say then that P max is equal to 1/2 times the magnitude of our Thevenin voltage squared divided by, or excuse me, multiplied by R Thevenin, and then divided by twice R Thevenin, right? Yes, you're correct. So let's see. So that's going to give us 1/2 times 1/4 is 1/8. So that's VTH magnitude squared divided by 8 R Thevenin. But we don't have VTH squared. So what do we need to do? This would be the same thing as 1/8 I Norton squared RTH, if we just do a transformation, right? Because we know that VTH is exactly the same as I Norton divided by I Norton is VTH divided by RTH, yeah. All right, so from this, P max is 1/8. Our magnitude of our current, 3.578 amps quantity squared times, now we need the resistance of our impedance, right? So I'm going to do that the lazy way. 1.470 cosine negative 17.103 degrees, right? Because if I have my impedance in polar form and I want just the real part, it's simply the magnitude of the impedance multiplied by the cosine of the phase angle. And from this, I get squared times 1.470 cosine negative 17.103. 2.248 watts. Would it matter at all if I accidentally did cosine of positive 17.103? Not even a little bit, right? Cosine of negative x is the exact same thing as cosine of x. So it doesn't matter whether I'm looking at the real part of the Thevenin impedance or the real part of the complex conjugate of the Thevenin impedance, because they're both equal to RTH. All right, so unless anybody has anything else they want to ask about, finishing up 10, 15 minutes early today. Anybody got anything they want to address? All right, I'll see you guys on Monday for half an hour. We will talk specifically about multi-frequency power analysis, which is ugly. I'll try to make it not super ugly, but it is pretty ugly. All right.